All right, if you're getting ready for your chemistry exams, you know there are some topics you just can't avoid. Today, we're going to break down two of the big ones, the speed of chemical reactions and the balance points they hit, which we call equilibrium. Let's jump right in. So, here's our game plan. First, we'll get crystal clear on the difference between reaction speed and reaction balance. Then, we'll dive into the rules for each. And finally, and this is super important for your exams, we're going to apply all this to real questions from WAEC and JAMB so you know exactly what's coming. Before we get into all the theory, let's start with a little puzzle. You've probably seen this in the lab, right? Powdered chalk fizzes up like crazy in acid, but a solid chunk just kind of sits there reacting slowly. Why? Just keep that question in the back of your mind because by the end of this, you will know the exact science behind it. Okay, so at the heart of today's topic are two really different questions. The rate of reaction asks, how fast is this thing going to happen? It's all about speed. Chemical equilibrium, on the other hand, asks, how far is this reaction going to go? That's all about finding the balance point. Let's tackle speed first. So, what are the control knobs we can turn to make a reaction go faster or slower? Let's get into the rules of reaction speed. So how do chemists officially define speed? Well, the rate of reaction is just the change in concentration, how much of a substance you have, over a certain amount of time. That little triangle symbol, delta. That's just science speak for change in. So we can look at how fast our starting ingredients, the reactants, are disappearing or how quickly our final products are showing up. Either way, it tells us how fast we're going. But why do rates change? The big idea behind it all is something called collision theory, and it's actually pretty simple. For molecules to react, they have to physically smash into each other. But here's the catch. Not just any old bump will do. It's got to be a successful collision. That means they have to hit each other with enough energy, we call that the activation energy, and in just the right position. So, if successful collisions are what we need, how do we get more of them? The first and easiest way is to increase the concentration. Just think about it. A crowded room versus an empty one. When you pack more particles into the same space, they're just going to bump into each other way more often. More collisions mean more chances for a successful one, and boom, a faster reaction. Now, temperature is a huge deal because it gives you a double whammy. First, when you heat things up, the particles get more energy, so they start zipping around faster and collide more often. But, and this is the really important part, those collisions are also way more powerful. A much higher percentage of them will actually have enough energy to break bonds and create new products. It's this 2-for-1 deal that makes temperature so effective. And this brings us right back to our puzzle from the start. With a solid lump of chalk, the acid can only attack the particles on the outside surface. But when you crush it into a powder, you suddenly increase the surface area a massive amount, exposing tons more particles. More particles available to react means way more collisions happening at once. And that's exactly why the reaction goes so much faster. Catalysts are kind of like chemical shortcuts. They are amazing because they speed up a reaction without actually getting used up themselves. What they do is provide a whole new, easier path for the reaction to take, a path with a lower activation energy. It's like finding a tunnel through a mountain instead of having to climb all the way over the top. For gases, pressure is really just another way of changing the concentration. When you crank up the pressure, you're literally squeezing the same number of gas molecules into a smaller container. That forces them closer together, they collide more often, and, you guessed it, the reaction speeds up. Okay, so we've got a good handle on speed. Now let's switch gears and talk about balance. See, some reactions don't just go in one direction. They can go forwards and backwards. And this is where we run into chemical equilibrium. The most important word here is dynamic. It's a really common mistake to think that at equilibrium, the reaction has just stopped. It hasn't, Not at all. It's just that the speed of the forward reaction, making products, is now perfectly equal to the speed of the reverse reaction, turning back into reactants. Imagine two people walking in opposite directions on an escalator. They are both moving, but their position on the staircase stays the same. That's dynamic equilibrium. Now, chemists have a way to measure this balance point, and it's called the equilibrium constant, or Kc. You can see, it's basically a ratio. The concentration of the products goes on top, and the reactants go on the bottom. So think about it. If Kc is a really big number, like 1,000, it means the top part of that fraction is huge. So the reaction loves making products. If Kc is a tiny number, like 0.001, it means the bottom part is bigger, and at equilibrium, you've mostly got reactants left over. So, what happens if we take a system that's perfectly balanced at equilibrium and we mess with it? How does it respond? Well, there's one incredibly powerful rule that lets us predict exactly what will happen. It's called Le Chatelier's principle. This is it. This is the whole idea. The system will literally fight back against whatever you do to it. If you add more of something, the system will try to use it up. If you take something away, it will try to make more of it. If you heat it up, it will try to cool itself down. It always works to undo the change and find a new balance. This table breaks it down perfectly. Let's say you add more reactants. The system says, whoa, too much of this stuff, and it shifts to the right to make more products and use it up. Or if you increase the temperature for a reaction that absorbs heat, that's an endothermic one, the system will shift to favor that direction to cool things down. And for pressure, the system tries to relieve that pressure by shifting to whichever side has fewer gas particles or moles of gas. It's all about pushing back. Okay, enough theory. Now for the part that really matters, using all this to actually score points on your exams. Let's tackle some real questions you could see. Here we go. A classic JAMB question. What does a catalyst actually do in a reaction? Think back to our rules of speed. Is it making that mountain taller or shorter? Is it slowing things down or speeding them up? The correct answer is C. It lowers the activation energy. But listen up. Here is the expert tip you have to remember for your exam. A catalyst speeds up the forward reaction and the reverse reaction by the exact same amount. This means you get the equilibrium balance point faster, but the final balance, that ratio of products and reactants, doesn't change one bit. That's a huge point they love to test. Let's try another one, this time focusing on equilibrium. We've got this reaction here, all gases. What happens if we crank up the pressure? Now remember Le Chatelier's principle, the system is going to try to reduce that pressure. How can it do that? And the answer is B, it shifts to the right. The logic here is all about counting the gas molecules. On the left side, the reactant side, you have 2 molecules of SO2 plus 1 molecule of O2 for a total of 3 gas molecules. On the right side, the product side, you only have 2. So to relieve the pressure, the system shifts to the side that takes up less space, the side with fewer molecules. In this case, that's the right side. So let's wrap this up. What are the absolute essentials? Reaction speed is all about successful collisions. We can control it with concentration, temperature, surface area, and catalysts. Equilibrium isn't a dead stop. It's a dynamic, active balance. And Le Chatelier's principle is your secret weapon for predicting how that balance will change. Let's end with a real-world challenge. Chemists use these exact principles to run massive industrial processes like the Haber process, which makes the fertilizer that feeds billions of people. Their goal is to get the most ammonia they can. So based on everything we just talked about, what conditions of temperature, pressure, and catalysts would you pick to make the most ammonia as fast as you possibly can? That is where this chemistry really changes the world. Great job following along. If you found this tutorial helpful, don't forget to subscribe to our YouTube channel for more easy to understand lessons. And hey, Want to practice more questions and get step-by-step solutions? Visit www.examkp.com right now and keep learning smarter.